for the future. I'll mention maybe some of those. But there are already very many exciting things happening now, and I just want to give a brief overview. There are plenty of things. I will not be able to cover everything, but feel free to ask any questions, either during the session or later on. So cosmology has been incredibly relevant for high-energy theory, broadly defined in the last couple of decades. And it is actually quite amazing that we can sit here and observe things on our past light cone. We mainly observe these small density fluctuations, the most famously the cosmic microwave background radiation, which is some slice in our past light cone at fixed distance or redshift. And doing these observations, we were able to discover or measure very precisely very many interesting things, such as dark matter, dark energy, and inflation, which in turn have a lot of are very important for the way that we see like the world, and they influence a lot the particle physics and string theory. And the reason why this is possible in cosmology, the two main mechanisms that allow this to happen is that, first of all, the universe as we see it today contains a lot of relics from some very high energies, because the universe evolved from some very high energy state, and you can say that in some sense whatever we see is some product of some very high energy process. And the second thing is that if you observe very large volumes, we can have a very good statistics, and we can find little effects that are otherwise hard to detect in laboratories. And so because we are probing these very high energies, I think that cosmology is the place where surprises are always possible. And if you look from the bottom up, using some kind of usual effective field theory logic, and for example, you have only data from the accelerators, you would probably not imagine that there is something like dark matter or inflation, simply because those things are not needed to maybe resolve the immediate problems that we have in experiments, but however, they're there on the sky. And so for this reason, I think that we should be always optimistic, and there is a chance always to find something that we did not expect, which then in turn will have some impact on high-energy theory. So let me now review a little bit some of these examples of these relics. Of course, the most famous one are the small density fluctuations in the cosmic microwave background. We see them as the fluctuations in the temperature and polarization of the CMB. And I will not spend much time talking about the CMB because you have heard this story probably many times. Let me just tell you that the current status and what are some plans for the near future. So the main things that are happening at this point are basically measurements of the polarization on small angular scales. And the main instruments that are now going to deliver a lot of new interesting data are Atacama Cosmological Telescope and South Pole Telescope. And here you can see some compilation of the most recent measurements from, let's say, or these are a bit old, by the way, now. I think that there will be major updates this summer, but these are measurements of the EE and TE power spectra. These are polarization power spectra. And you can see that these instruments, the important point that I want to make here is that the Planck error bars are these blue like error bars here, and these instruments are already measuring polarization much better on small angular scales, measuring more acoustic peaks. In the future, they're going to basically measure cosmological parameters better than Planck just from polarization measurements. There will be some improvement. This improvement will not be dramatic. We're talking about factor of 2. But there will be an improved results, and I think that ACT is supposed to release their data this summer. Okay. Now, one very interesting point that remains always one of the great goals for this program is to measure the amplitude of the primordial B modes, which are related to the tensor to scalar ratio R, or which is in turn related to the Hubble parameter during inflation. And here I'm showing the projected constraints for one of the approved satellites, Lightbird. And we can see that we are going to improve these bounds by 2 orders of magnitude compared to where we are now, which means that we are going to improve the maximum value of Hubble parameter during inflation by an order of magnitude roughly in the next 10 years. And I think that this is probably the single most interesting parameter to know if you want to talk about the relation of cosmology to string theory, because in principle, these are the highest energy scales that we can probe in our universe. And it will be good to know if we are there, but like it would be, of course, amazing if we could see something. But even if not, I think that there are other things that we can look at. And the best example are probably primordial non-Gaussianities, where we are looking for some little hints of some new physics in correlation functions beyond the two-point function. And so if you compute in various inflationary models, you can compute the three-point correlation function of the so-called curvature fluctuation, which are related to the temperature anisotropies in the CMB. And this three-point function then has some dependence on the three momenta, which we usually call the shape of the non-Gaussianities. There are two phenomenological templates that people often use. One, which basically peaks when one of the momenta is much smaller than the other two. So in this soft limit, if you have a template which peaks, has the most of its amplitude in the soft limit, then this shape is called the local shape, and its amplitude is proportional to the parameter that we call FNL local. While if, for example, the bispectrum is such that it vanishes in this limit, but for example, it peaks when all the momenta are similar size, this is called equilateral template, and it's proportional to this parameter, which we call FNL equilateral. And the reason why people look into these two numbers in particular is because they can, in a very model-independent way, tell us something about the dynamics of the fluctuations during inflation. So in the simplest vanilla single-field models, the local non-Gaussianities are equal to 0, so basically there are no local non-Gaussianities, and then equilateral non-Gaussianities are proportional to slow roll parameters. So they're, for all practical purposes, basically unobservable. And this is great because then, in a very model-independent statement, if you measure one of the two, we can say something. And in particular, seeing some local non-Gaussianities means that we are not in the single-field inflation. So this means that there are other active degrees of freedom which contribute to the density fluctuations we observe in the CMB. While seeing some equilateral non-Gaussianities means that we do not have some conventional, simple kind of field theory that we would naively write down, but that inflaton fluctuations propagate with a speed which is smaller than the speed of light. This is possible because the inflaton background spontaneously breaks Lorentz symmetry, so nothing prevents this from happening. And these are two very model-independent statements that you can make, which are related to data. The current best bound from Planck on these parameters are around 5 and 15. Now, even though the CMB was very important for cosmology and and basically brought us to this stage of precision cosmology, there are many open questions, and here I'm mentioning some of those related to maybe high energy theory that CMB cannot help us answer to. Okay, so I told you that in the simplest inflationary model, non-Gaussian is small. However, if you look at various extensions which are plausible, you will find that typically these FNL parameters are of order 1 or larger. So generically, we would say that we expect to see some deviations from a perfect Gaussianity in the sky. There is a big question about scalar fields in cosmology, and this, of course, includes the inflaton, dark energy, possibly axions, and other things. And I will say that basically there are questions, as we saw also in the previous talks, that we cannot answer using the CMB alone. Another interesting question, maybe related to inflation, is like, what is the curvature scale? Like, what is the value of the curvature of the universe? Of course, in the simple, again, way that we explain inflation, this curvature scale should be 0. But if inflation doesn't last too long, maybe the curvature is not really 0. And so the current CMB alone bound of the curvature is 1%, roughly speaking. But there are targets that I'm going to discuss as well, which are smaller than these, which are interesting to reach, and the CMB cannot do it by itself. And also, we can ask about some primordial features in the power spectrum even. This could be some features like small oscillations in the inflationary potential, or it can be some features on very large scales related again to the duration of inflation, or maybe some corrections to, let's say, simple de Sitter a semi-classical picture that we have for whatever reason that we maybe don't know at the moment. So these are all open questions for which we need to look elsewhere. And so for this and many other reasons related to other things that I'm not going to talk about, there is this very big observational program where people are trying to measure fluctuations not only far away in the CMB, but also on the entire past light cone. And the idea for the next decade or so is to measure to take images of billions of objects in the sky and measure spectra of hundreds of million objects all the way up to redshift 5. And roughly speaking, these big so-called galaxy surveys are split into two types, like photometric surveys and spectroscopic surveys. And like here, I'm showing some timeline, and these points indicate when do these missions start. So we are here now in 2024, and basically DESI and Euclid are already operational, and they're collecting data. DESI has collected already half of its data. We are expecting the first light for Rubin Observatory, which was also maybe known as LSST to you. And then next year, we're expecting the launching of SphereX, which is a satellite, and which will start collecting the data in a year or two. So you see, there are a lot of things happening, and there will be a lot of data collected in the next couple of years. And by the end of this decade, the landscape of cosmological data set is going to change dramatically. So I cannot talk about all of these surveys, but let me maybe just give you a little bit more detail about a particular type, the so-called spectroscopic galaxy surveys. They're called spectroscopic because we are measuring spectra of each individual galaxy, which allows us to make these nice maps where you can see this cosmic web. So this structure, of course, is not random. It remembers the initial conditions, and this is the main point. Those fluctuations are basically the same as the CMB fluctuations, just evolved in time. So you can still use them to say something about the entire history of the universe. We are very good in making these maps. In fact, this is a very long program, and you can see here that basically we increase the size of the spectroscopic sample, which is the number of galaxies that we measure spectra for, by a roughly factor of 10 every decade. And I would argue that the currently ongoing surveys are a bit special because they're expected to have similar amount of information as the CMB itself. So the reason why this is now interesting is because we are going to have two similarly powerful probes at very different redshifts, and in combination they can give us a lot when we use them together. Now, let me maybe comment a little bit about some things that have been done already and some things that are may be familiar with. And just to illustrate the point, like when I told you that this distribution of galaxies is not random, but it actually remembers the initial conditions, one way to see this, for example, is that you measure the two-point correlation function in real space of the fluctuations of galaxies. You will see that there is a nice peak at some fixed distance of around 100 H inverse megaparsecs, and this is the famous baryon acoustic oscillation peak. It is set in the early universe, and it has to do with the propagation of the sound waves in primordial plasma. And what is nice about it is that we understand its physics very well. It is very easy to measure in the data. It's hard to confuse with some systematic things, and very easy to model theoretically. And so basically, from the measurements of the angle under which you see this feature in the given redshift, you can basically measure the entire expansion history of the universe. And this has been used recently in this DESI data. Of course, this can be done also in the past, but the most precise data that we have are the DESI data. You can see that they find the acoustic feature in different redshift beams, and combining all these redshift beams, they can put constraints on basically this function here, which measures in some sense the expansion history. And this function, of course, depends on various things like omega matter, curvature, and possibly some dark energy equation of state. And so for each cosmological model, you can then use the combination also with the other data to measure these cosmological parameters. We have already seen some of these plots, and I will comment about it later on. Let me just say that, for instance, when we talk about spatial curvature, the best constraints we have to date are really not coming from CMB. They were 5 times larger, the error bars, but really it's crucially, we have to include the baryon acoustic oscillation data in this discussion. Okay, now this is all great, and we can continue doing it, and it will for sure be happening, but we can do actually much better than that. So measuring the baryon acoustic oscillation peak is just measuring one single feature in the two-point function, and there is much more information in the full shape of the two-point function. So it is a bit like we can ask, can we use galaxies the same way as we use the CMB, where we take the map and then measure all endpoint functions in principle and try to feed them directly with some cosmological model. So the answer is yes, and it has been a lot of progress recently. And of course, the key ingredient that you need in order to do such exercise is some reliable way to model all these complicated nonlinearities that galaxy fluctuations depend on. I will not go into any details, but I will just tell you that there is a very nice way to actually do it on large scales, applying these effective field theory methods. And it allows us that on large scales, larger than basically typical intergalactic separation, we can find the description which is a universal description of galaxy clustering, and all three parameters in this description, like in any effective field theory, will depend on some details of like microphysics of particular processes that involve galaxy formation and so on. Now, of course, there was a lot of work in this direction to make this actually possible, and these days we have put all of these things together into several publicly available, let's say, codes which you can use to compute really the real observables, things that you see on the sky, given some cosmological model, including all this nonlinear evolution. So this allows us to really make a revolution similar to what was happening with the CMB, where we can explore various cosmological models, but using the full information in the data in the late universe. And this is a big step forward, which allowed us now to do many things that were considered impossible just like 5 years ago or so. So let me show you, for example, what happens when you apply these methods to the currently best galaxy survey that we have, for which the full data is publicly available, which is BOSS. What you should take a look at are these basically red contours in this contour plot. These are the Planck measurements of the cosmological parameters, and the blue contours are BOSS measurements of the cosmological parameters. And you can see that, of course, for some things, the CMB is still quite better, but some parameters, such as the Hubble parameter or omega matter, are measured with similar precision. However, here, the galaxy clustering data do not use any input from the CMB. So these are two independent measurements, and it is very nice that they agree, and more interestingly, maybe they have similar error bars. So we can already exploit currently existing data in these interesting ways, and I think that the future will be, of course, much brighter. And now, I would like to go through a couple of examples of what we can do with let's say, something like full DESI or Euclid galaxy survey. So regarding primordial features and primordial non-Gaussianities, things will improve quite a bit. For instance, for local non-Gaussianities, we know that we can reach this threshold of FNL of order 1, and this will happen by the end of this decade. We're going to have measurements which are going to be like, which will cross this interesting threshold, which basically is the boundary between single field and multi-field models. The other type of non-Gaussianities remain challenging in the sense that it will be hard to get to FNL quarter of order 1. However, there will be a big improvement from future surveys compared to the Planck error bars, which here are given these orange contours. There was a lot of discussion, and I think that we were going to talk also about it later, about dark energy and perhaps spatial curvature. And let me just say here that also for these two parameters, things will improve quite a bit. So what I try to show here is basically some forecast for the full DESI mission of full 5 years. And here is the cartoon, which is not very successful. I think that these contours are a bit too thick, but the size is approximately right of what kind of error bars do we have today, okay? So what is interesting here to see is that these parameters will be measured almost as well from DESI alone as they're measured today through a combination of all possible data sets. And I think this is an important message because we will know if there is a real discrepancy with respect to CDM or not. Similarly, curvature constraints will improve by, let's say, at least 1 or 2 orders of magnitude. And here, I think that we're going to reach this interesting threshold where basically we do expect some curvature eventually, which simply comes from the very long wavelength fluctuations in our universe. And these long wavelength fluctuations have the amplitude roughly 10 to the minus 4. So once we get to this limit, I think that then seeing zero curvature is not necessary anymore. But it is, I think, interesting that we can actually get there with these galaxy surveys. Any hint of, let's say, some open universe or something like this would be, of course, very interesting because it would be an indication that immediately there will be a lot of speculation about it. For example, that maybe you start inflating after some tunneling, or like you have just enough e-folds of inflation because it is hard to sustain inflation for a long time, and so on and so forth. So this will be probed by this data in detail. And so finally, let me just in the last 2 or 3 minutes tell you about something a little bit different, which also I think can be related to string theory, of probing, for example, things like ultralight axions with cosmology. So here the idea is that if you have axions which have very small mass, then you can actually see their effects on cosmological scales. It turns out that there is a nice numerology which basically tells you that if you have like axion mass, which is relevant on cosmological scales, and you have the decay constant, which is somewhere between the God scale and Planck scale, then the abundance of such axion in our universe will be close to the dark matter abundance. And so we know that basically these masses are ruled out as the 100% of dark matter, but of course it is always possible to have some fraction of dark matter in these ultralight axions. And the mass range that cosmology can very well probe are these masses, which are of course arguably very small, but perhaps we have some, let's say, fraction, let's say 1% of dark matter or so, given this numerology, which is in these ultralight axions. And so the CMB constraints at the moment are actually, it turns out, for a big fraction of this mass range, are weaker than the current Bose constraints from large-scale structure. If you look at this analysis in detail, you will see that the CMB has this strong degeneracy of the axion fraction as a dark matter with a Hubble parameter, while large-scale structure measure it a bit more directly. The physics here really is that on scales smaller than the de Broglie wavelength, there is no clustering of this percent of dark matter, and so therefore you will see some different level of clustering in galaxies, let's say on different scales, and this allows you to put these nice bounds, which then in the combination of the CMB gives us the tighter constraints. Soon enough, with DESI data, these bounds will improve by another order of magnitude. So there will be really like a big jump forward. So let me then just conclude, because I'm running out of time. I think that there will be like clearly a huge amount of new data in the coming years. We have new ways to analyze this data to really fully to squeeze all the available information and test not only some simple extensions of lambda CDM, but many other models which are potentially interesting. And in all directions, we see that there will be many order of 10 improvements on various cosmological parameters. And so for any of these scenarios, you may say, well, this is very unlikely, and it is true that we may just find lambda CDM at the end of the day. But as I said at the beginning, surprises are always possible, and I think that now it is a good time to maybe be excited about it and try to think about what are the things that we can possibly do with this data. So I stop here and take questions. Thank you.
Thanks, Marko, for a very nice talk. Miguel.
Thanks. So the bound that you gave for V prime over V less than 0.05, that's after inflation, right? It's not during inflation.
Yes, I'm talking about the dark energy. Yes, these are the best possible constraints that we can hope to have, let's say, until 2030.
And this will come from fitting the whole curve of the...
This will come from fitting the whole data, yes,
okay.
yes.
Thanks.
Jacob?
Thanks for the very nice talk. Can you say a few words on the prospects of detecting CP violation in the CMB, like cosmic birefringence? Is that what's the status?
So, well, there are several things. I think that if you mean CP violation, I'm not entirely sure because there was a parity violation in the 4-point function, which turned out not to be really there. Look, there was a parity violation of the 4-point function, I think, in the large-scale structure data, which turned out to be due to some little systematics, which went away. There is a cosmic birefringence, which has to do with, like, of course, having some additional coupling of the photons to, let's say, the scalar field in between as they propagate. Yes, those are measured from the EB correlation functions. And I think that those will improve a lot with these new data from, let's say, Simon's observatory or polarization measurements. I don't know on top of my head how much, but they will improve. Yeah.
Yes.
In 2014, BICEP published the primordial B modes were detected and this was fake. Does your community know how to subtract foregrounds properly?
Well, it depends on the level of foregrounds. Like I think that they were a bit too fast. The reason why I think also there was a confusion back then is that there was some expectation in the community which was wrong, based on some astrophysical simulations. I think that people are much more. I mean, like, of course, they saw a big signal, so they were a bit confused by that. If you go to the smaller signals, you will be much more careful. And I think that foreground subtraction, in principle, is not so difficult. We do it for the CMB all the time. The B mode is not very different. I think that if you're careful enough, you can do it. Up to this 10 to the minus 3 level, then it becomes very hard.
Daniel?
Yeah, hi. So given the issues with CMB stage 4 in the South Pole, how much uncertainty does that put into the story you're telling us about the next 10 years? I mean,
well,
what is CMB stage 4 now?
I think that there are certainties about CMB stage 4, but anything I said here is certain. So I never used, this never includes any CMB stage 4. I think that Lightbird is funded and it will fly. If you want stage 3.5, which is Simon's Observatory, will happen. And all these large-scale structure surveys will happen. So altogether, I think that they will be as good as having stage 4. So that I don't think there is a major issue with this.
But so say if some version of CMB4 light or stage 4 light happens in Chile or something, does that substantially change the story you were telling?
No, I don't think so. I think that the CMB itself will improve things a little bit because all that you gain is polarization. At most, you can gain factor of 2, like in the number of modes and so on and so forth. What is really different is that using large-scale structure, this is what gives you a factor of 10, because these are completely different data, which then in combination with the CMB are super powerful in constraining things. So I don't think that for any of these constraints or any results I mentioned here, whether CMB stage 4 happens or not matters.
Could you say a few words about the prospects for measuring the neutrino masses?
Yes, I did not. I think that I have somewhere the plot. Let me show you. So the neutrino masses will be measured as well by something like Euclid or DESI survey. What you should look is these contour plots here. So if neutrino masses was 0.1, let's say, electron volts, this would be the Mach Planck constraints, these dashed blue curves. And you can see that the red contours, which will be the analysis of the power spectrum of DESI or Euclid-like survey, will confidently measure the sum of neutrino masses, even if they're sitting at the lowest possible mass. So I think that we can expect 3 sigma measurement of the neutrino mass, even if it is 0.06 electron volts from this date.
Yes, Fernando?
Very nice talk, Marko.
Thanks.
Yes. How much can you push, in principle, the limits on R and omega k? Say, not in 5 years or 10 years, but further away.
I think that the curvature, so basically there are 2 ways from where curvature constraint comes from. One is that in the curved universe, of course, fluctuations behave differently. But that is a small effect, which is hard to disentangle from the rest of the nonlinear evolution. The other source of information comes from really the expansion history as measured through this BAO and so on and so forth. So basically, those are not going to improve dramatically, I think, beyond what we can do with these future surveys. We are going to get to, let's say, 10 to the minus, between 10 to the minus 4, 10 to the minus 3. I'm not entirely sure. It depends a bit how optimistic you are and what kind of data sets do you combine. But we will come close to the level, as I said, where you expect some curvature simply from the long wavelength fluctuations. And R, I think, with the Lightbird, will go to 10 to the minus 3. Beyond that becomes very difficult, given the level of foregrounds, even for the future experiments.
I believe we have a question from Zoom.
Yes. It was just related to your slide on the open questions. I think so. The question is that there you mentioned scalars and axions, and how about gauge fields?
Yes, I think that, well, the gauge fields, I think that there is an interesting phenomenology. For example, if you have inflaton coupled to some gauge field, you can produce gravitational waves. You can produce primordial magnetic fields. There are all these things. I think that those are mainly inflationary related questions, which are, again, not going to change dramatically with large-scale structured data. So galaxy clustering is not good to measure those things. So the latest CMB measurements will improve things, but I think that within the factors of 2, again, these are the...
Okay, so I think we should thank Marko
Thank
again
you.
for a beautiful talk. And I think we now move to Michelangelo Mangano, who's going to tell us about connections with particle physics.